We're solving problem 25 from the 2020 AMC 12B. For each real number a with a is greater than or equal to 0 and less than or equal to 1, let numbers x and y be chosen independently at random from the intervals 0, a and 0, 1 respectively, and let p of a be the probability that sine squared of pi x plus sine squared pi y is greater than 1. What is the maximum value of PA? Now the first thing we can do is sort of rearrange this equation, and what we get is, well, if we just do subtract sine squared pi y from both sides, you get sine squared pi x is greater than 1 minus sine squared pi y. And we already know from basic trigonometric identities that this right here has to be equal to cosine squared pi y, because on the unit circle, we know that cosine squared of pi x whatever, cosine squared of whatever is inside, plus sine squared of whatever is equal to 1. So we have this. Now we want to consider the case where sine of pi x is equal to plus or minus cosine pi x. If this were true, then that means this could be simplified, cosine part could be simplified to sine of 1 over 2 times pi plus or minus xy. Now, solving for two cases here, for the first one, you're going to get y equals 1/2 minus x and y equals x minus 1/2. For the second case, you're going to get y equals x plus 1/2 and y equals 3/2 minus x. So we hence see that, well, if you just draw the figure here, like the square, this point is 0, 0. This point is 1, 0. This point is 1, 1. And this point is 0, 1. We're going to have some sort of diamond in the middle. And we have like the points A that make a line A, 1 and A, 0. So what we notice from this, although it looks slanted, if we just imagine it's a square, we're going to find that A, to maximize the probability of this being greater than 1, we know that A has to be greater than or equal to 1/2. Now, to maximize something, you first can reverse the things by minimizing some other factor. So let's call that other factor Q of A. Now we see in this geometric interpretation, the inside, this pyramid is the maximization that we want. So therefore, the minimization is the area outside. These two, now there's 4 triangles. So there's obviously these 2 triangles which are untouched by the line, and then these 2 spaces which are harder to denote. So if we call this minimizing space Q of A, where this is equal to 1 minus P of A times Q of A, then Q of A is equal to, well, you want to sum the area. So we have those 2 triangles, which have combined area of 1/4, and then this side, which first you want to divide by A, and then the inside is the sum of the areas. So this is going to be 1/4, the 2 triangles, plus, well, this is going to be our length A, and then subtract from it 1/2 squared, because you're taking away that much area. This can be simplified on the inside. Just multiply everything out to get 1/4 plus a squared minus a, or a, this is actually a 2, because you subtract another 1/4 from it, and then this would be a plus 1/2a minus 1. And by using the AMGM inequality, we get that a plus 1/2a has to be greater than or equal to 2 times the square root of a/2a, where this side simply simplifies to the square root of 2. Now notice this inequality, what we basically solve for is when they're equal, a has to be at least root 2 over 2. So therefore, our answer is going to be simply just the 1, then subtract from it the square root of the 2 minus 1, or 2 minus root 2. So that is our answer for this problem.